Think about the power of precise communication. I mean, in most situations, a small mix-up, maybe a minor hassle.
Right. Annoying, perhaps, but usually fixable.
But when you're talking about an aircraft, something complex, flying miles high, a single wrong word, a misplaced comma in instructions, the consequences are just unimaginable.
Absolutely.
Yeah.
Which is why we're doing this deep dive today into, well, what you could call the draftsman's language, aircraft drawings.
Yeah, the absolute bedrock of aviation engineering, construction, maintenance, everything, really.
They really are. These aren't just, pretty pictures. They're a highly evolved, standardized system. It's all about conveying super intricate details for building and assembling aircraft.
It's how an engineer's idea becomes a real physical flying machine.
And how it stays safe year after year.
Exactly. And for this deep dive, you've pulled together material from a chapter that really focuses just on this world, right?
That's right. It covers the whole journey. From, the old drawing boards, meticulous hand drafting, right up to modern computer graphics,
Right.
CAD systems and all that.
And it gets into the nitty-gritty, the conventions, the symbols.
Everything. The symbols, the lines, what they all mean. It's a universal language within aviation.
Okay, so what's our mission today for the listener?
Well, the goal is to give you a solid grasp of the fundamentals. We want you to feel comfortable looking at these drawings, understand the core information they're showing.
Without getting totally bogged down in, every single technical spec.
Exactly. To appreciate the precision involved, but not feel overwhelmed. Get those aha moments.
All right, let's unpack this. The chapter starts with that huge shift, doesn't it? Away from the traditional drawing boards to, the digital age.
Oh, yeah, a massive transformation.
We're talking CAD, CAM, CAE. It's a bit of an alphabet soup.
It sounds like it, but each one was a major leap. So CAD is your basic computer-aided design. Then you have CAD, often adding drafting features. CAM uses the digital design to actually run the manufacturing machines.
Right, computer-aided manufacturing.
And CAE, computer-aided engineering, lets engineers simulate and test the design virtually.
So what were the real game changers here? The big advantages of going digital?
Well, think about it. Suddenly you could visualize the entire aircraft in virtual reality. You could check if thousands, literally thousands, of parts fit together perfectly before making anything physical.
Wow. Instead of finding out on the assembly line.
Precisely. And you could share these incredibly complex designs instantly, globally. No more waiting for blueprints to be printed, rolled up, shipped out.
That speed alone must have been revolutionary. The chapter mentions big names like Boeing, Airbus, using software like CATIA.
Yes, CATIA is a major one. They essentially build the whole plane virtually first. Every single component, down to the last rivet.
That's mind-blowing.
And it doesn't stop at design. That digital blueprint can directly drive the machines that make the parts. Computer-controlled manufacturing.
Which cuts down on human error in reading the drawing.
Dramatically. Plus, think about the maintenance crews. Now they can pull up these super detailed drawings on a laptop or a tablet right there next to the plane.
Yeah, no more lugging around giant paper sheets in the hangar.
It's just a huge leap in accessibility and efficiency.
So whether it ends up printed out like an old-school blueprint or stays digital on a screen, the core function is the same.
Oh, exactly.
It's that vital link between the designers, the engineers, with the ideas.
And the skilled people actually building, fixing, and maintaining the aircraft. These drawings are the instructions, the definitive source.
The chapter even mentioned the old blue and white prints, the diazo process.
Yeah, the classic blueprint look. Now it's mostly inkjet or laser printers, large format plotters for the big sheets, all driven by digital files. But the principle holds.
And the need for care in handling them.
Oh, absolutely.
Yeah.
These documents are incredibly valuable. Any damage, any stray mark could lead to a misinterpretation.
It mentioned rules like don't spread them on dirty floors, no scribbling notes on them unless authorized.
Because that unauthorized note, that smudge, could obscure a critical dimension or detail. Think about it, the drawing number itself. It's like the part's ID. Without that precise number, tracking changes across a whole fleet. Impossible. You could end up putting the wrong version of a part on a plane.
Yeah, that sounds like a nightmare scenario. They have to be pristine.
Pristine and accurate. They are the authority.
Okay, so the chapter then breaks down the main types of drawings. 3 main classes, it said. Detail, assembly, and installation drawings.
That's right. Let's take them one by one. Detail drawings,
Yeah.
small scale. They focus on just one single part.
Like one bracket or one gear.
Exactly. And they give you everything you need to make just that one part. The exact size, the shape, the material, any special finishes or treatments, all the manufacturing specs.
So pretty straightforward, usually.
Relatively, yes. And if the parts are small, you might even find drawings for several different small parts grouped together on one sheet.
Okay, makes sense. Individual building blocks, then assembly drawings.
Right, assembly drawings show how those individual detail parts fit together. They depict an object made of two or more parts.
So moving up a level, like how the gears fit into the gearbox.
Perfect example. The focus shifts to the relationship between the parts, how they connect, their relative positions. These are naturally more complex than detailed drawings.
And they probably refer back to the individual detail drawings for the specs of each piece.
Often, yes, they work together. The assembly drawing shows the big picture of how things join. The detailed drawings provide the specifics for making each piece.
Got it. Showing how all the engine bits, say, come together to make the whole engine unit. And the third type, installation drawings.
Installation drawings take it one step further. They show how that completed assembly, like our whole engine unit, gets put into the aircraft itself.
Ah, okay. Mounting the engine onto the wing, for instance.
Precisely. These drawings give you the critical dimensions, the reference points on the airframe, the attachment hardware, everything needed to locate and secure that assembly correctly within the larger structure.
So it's like a hierarchy. Smallest part, then subassembly, then how the subassembly fits into the whole aircraft.
You got it. A logical breakdown from micro to macro.
Now, another thing was showing what's inside a part. The chapter talked about sectional views, cutting things open visually.
Yes, sectional views are crucial. Sometimes the important stuff is hidden inside. A sectional view lets you see that internal construction.
It mentioned cross-hatching.
Right. Imagine you slice through the object with a saw. The surfaces where the saw cut the material are marked with those diagonal cross-hatching lines. It clearly shows the internal shapes.
Okay, and there were different types of sections, like a full section.
A full section is like slicing completely through the object along a specific line, removing the front part and showing the entire internal view. The cable connector example was good. You need to see inside to understand the wiring.
Makes sense. Cut it right open. What about a half section?
A half section is clever, used mainly for symmetrical objects. Imagine cutting only halfway through to the center line.
So you see half inside, half outside.
Exactly. On one side of the center line, you see the internal construction, cross-hatched. On the other side, you see the normal exterior view. The capstan servo example showed this great for seeing both internal workings and the outside shape in one view.
Efficient. Saves drawing space too, I bet.
It does. Then you have revolved and removed sections.
Okay. What are those?
A revolved section is for showing the cross-sectional shape of something long and thin, like, say, the spoke of a wheel or the arm of a lever. You slice it, then rotate that shape 90 degrees and draw it directly on the main view.
Ah, so you see the profile right there on the part.
Yep. A removed section, though, is when you take that cross-section view and draw it off to the side somewhere else on the drawing, often at a larger scale.
Why do that?
To show more detail. If the cross-section is complex or needs clearer dimensioning, you pull it out, maybe enlarge it, and label it clearly, like section AA, referencing where the cut was made on the main view.
Gotcha. Like zooming in on a specific internal slice for extra clarity. Now, every drawing needs an ID, right? That's the title block. Sounds critical.
Oh, it's absolutely fundamental, usually tucked away in the bottom right corner. It's the drawing's passport, essentially.
What kind of information is in there?
Always the drawing number. That's key for filing, finding it again, tracking changes. Then the name of the part or assembly. The scale the drawing is made to. The date. The company name.
And the people involved.
Yes. Usually the names or initials of the draftsman who drew it, the checker who reviewed it, and the engineer who approved it. Accountability.
A complete little data package for that specific sheet. You mentioned the drawing number. The chapter also talked about drawing and print numbers and how they handle multi-sheet drawings and dash numbers.
Right. So the main number identifies the drawing overall. But complex drawings often need more than one sheet of paper.
So how do you keep track?
Each sheet will have the main drawing number plus a sheet number, like sheet 1 of 4, sheet 2 of 4, and so on. Pretty simple.
Okay. And dash numbers.
Dash numbers are used when one drawing actually shows several very similar but slightly different parts. A common use is for left-hand and right-hand versions of the same component.
Ah, like a bracket for the left wing versus the right wing.
Exactly. Instead of two separate drawings, you might have drawing number 1, 2, 3, 4, 5, and then part 1, 2, 3, 4, 5, 1 is the left-hand one, and 1, 2, 3, 4, 5, 2 is the right-hand mirror image part.
Saves effort. Does it always show both?
Often, they'll just draw the left-hand part in full detail and make a note saying the right-hand part neck is 2 is opposite, or a mirror image. Sometimes they use odd dash numbers for left and even for write.
Smart. Says repeating identical information. The title block might also have reference numbers, pointing elsewhere.
Yes, reference numbers can link this drawing to other related drawings, maybe the next higher assembly or a specification document. It creates a traceable web of information.
And then there was the universal numbering system for drawing sizes, like paper sizes, A, B, C, D, E.
Yeah, or sometimes numbers like 1, 2, 4, 5. It's just a standardized way to classify the physical size of the drawing sheet itself. Helps with filing, printing, storage.
Like A size is standard letter paper, B is tabloid, and they get bigger.
Pretty much. An A or 1 is typically 8.5 by 11 inches. A B or 2 is 11 by 17. It goes up from there. But, as the chapter noted, companies might tweak the system for their own needs.
So a standard starting point, but adaptable. This all falls under drawing standards, right? Which sounds like a massive rule book covering everything.
It basically is. These standards, often from organizations like ISO internationally or ANSI in the U.S., dictate everything.
Like what?
Oh, paper sizes, how drawings are numbered, the precise appearance of different line types, how singles are drawn, how tolerances are written, you name it.
Why so rigid?
Consistency. Think about global supply chains. A part might be designed in the U.S., manufactured in Europe, installed in Asia. Everyone needs to read that drawing exactly the same way. Standards prevent chaos and costly mistakes.
Makes sense. Now, besides the lines and shapes, drawings often have a bill of material, or BOMOM. You call it a shopping list.
That's a great way to think of it. It lists everything needed to make or assemble what's shown on the drawing.
Like raw materials, specific nuts and bolts.
Exactly. It'll typically have columns for the part number, the name or description, the material specifications, how many are needed, quantity, and maybe even where to get it, or the standard it conforms to.
Super practical, like the recipe for the part.
Precisely. It might be a table right on the drawing, or sometimes included as a separate document referenced by the drawing.
Okay. Then there was a section on other drawing data. Lots of important bits and pieces here, starting with the revision block. This seems super critical.
Absolutely crucial. Aircraft have long lives, and designs get updated, improved, corrected. The revision block, or rev block, tracks every single change made to that drawing after it was initially released.
So if they change a dimension or the material,
it gets documented there. Each change gets an identifier, like Rev A, Rev B, the date, a brief description of what changed, who authorized it, and who incorporated the change onto the drawing.
So you always know you're looking at the latest approved version.
And you have a history. You can trace the evolution of the part. Essential for configuration management and safety.
Okay, what else was in other data?
Notes.
Notes are for everything else that can't easily be shown with lines and symbols. Special instructions, maybe alternative part options, assembly procedures, finishing requirements.
How are they shown? Just text on the side.
Sometimes grouped together in a general notes section, referenced by number, or sometimes placed right near the feature they apply to, with a leader line pointing to it.
Got it. And then things got really specific with location identifiers on big aircraft. Zone numbers, station numbers.
Yeah, for large structures like a fuselage or wing, you need a precise way to say where something is. It's like a coordinate system for the aircraft.
So zone numbers are like grid squares on a map. Sort of, yeah. They break the drawing, especially large ones, into zones, like A1, B5, so you can quickly reference a general area. Easier than saying, look in the upper left corner.
And station numbers, fuselage stations, buttock lines, water lines. Sounds like shipbuilding terms.
Some origins might be shared, but an aircraft. Fuselage stations, FS, measure distance along the length, usually from the nose backward, in inches. Buttock lines, BL, measure distance left or right of the aircraft's vertical center line. And water lines, WL, measure vertical height from a reference plane.
So FS, BL, WL gives you a precise 3D coordinate for any point on the aircraft.
Exactly. Wings and stabilizers have their own similar station systems too, measured from their root or center line. It's essential for locating components, repairs, anything.
Incredible precision. Speaking of precision, allowances and tolerances, this is fundamental manufacturing stuff, right?
Absolutely fundamental. They control how parts fit together. Allowance is the intentional difference between the dimensions of mating parts. It dictates the type of fit, like a loose fit where parts move easily, or a tight interference fit where you need force to assemble them.
Okay, so allowance is planned space or interference. What's tolerance?
Tolerance is the unavoidable but acceptable amount of variation allowed in the dimension of the single part. Manufacturing isn't perfectly exact.
So the drawing says maybe 0.225 inches, but there's a plus minus.
Right. The example was 0.225 plus 0.000005. That means the actual part can be anywhere between 0.2245 inches and 0.2275 inches and still be acceptable.
And the difference between those limits, 0.003 inches, is the tolerance.
Exactly. It allows for slight manufacturing variations while still ensuring parts will interchange and function correctly. Too tight a tolerance is expensive, too loose, and things don't fit or work.
Crucial for making sure replacement parts actually fit.
Absolutely. Without proper tolerances, mass production and reliable repairs would be impossible. Even tiny deviations outside tolerance on, say, a flight control surface hinge could be critical.
Then there were finish marks indicating machined surfaces.
Yes, specific symbols that show a surface needs to be machined smooth for a better appearance, or more importantly, for a precise fit with another part. It's different from just paint or plating.
And scale, always trust the written dimensions, not just how big it looks on screen.
Always. Always trust the dimensions written on the drawing. Especially with CAD, you can zoom in and out, which changes the visual size, but the dimension value stays the same. The scale notation, like 1.1, 1.2, tells you the intended ratio, but the numbers are king.
And finally, application, just making it clear what this drawing is for.
Right. Specifies which aircraft model, which assembly, maybe even which specific serial number range or modification status the drawing applies to. Vital for making sure you use the right drawing for the right job.
Okay, that covers a lot of the metadata on a drawing. Now, how about the actual ways things are illustrated? Methods of illustration, started with applied geometry.
Briefly, yeah. Applied geometry is the mathematical foundation, the rules behind creating accurate graphical representations. It used to involve T-squares and triangles. Now it's embedded in the CAD software.
But the main method discussed was orthographic projection, multiple views.
Yes, this is the cornerstone of technical drawing. It's how you represent a 3D object accurately on a 2D surface.
How does it work?
You project views of the object onto imaginary planes at right angles, typically the front, top, and right side views. Then you arrange these 2D views in a standard layout on the drawing.
So you can see the exact shape and size from different angles.
Precisely. It removes ambiguity. Depending on the object's complexity, you might use 1, 2, or the standard 3 views, sometimes even more if needed.
Like unfolding a box to see all its sides flat.
That's a great analogy. It lets you measure accurately from the drawing.
And sometimes you don't need all 3 views.
Right. For simple, flat parts like a shim or gasket, 1 view plus a note about the thickness might be enough. For symmetrical parts, you might use a half view, showing only half the object relative to a center line.
And a detail view, is that different from a detailed drawing?
Good question. A detail view is a small portion of a larger view blown up to a bigger scale to show intricate features more clearly. You'll often see a circle around an area on the main view labeled Detail A, and then elsewhere on the sheet you'll find Detail A drawn larger.
Got it. Zooming in on a complex bit. Then we move to pictorial drawings. These look more like pictures, right?
Yes, they aim for a more realistic 3D appearance. Easier to visualize the overall shape, especially for people less familiar with reading orthographic views, commonly used in maintenance manuals.
What types are there? Perspective.
Perspective drawings try to mimic how our eyes see, with parallel lines appearing to converge at a distance. They look realistic, but aren't dimensionally accurate for measurement.
Okay. Isometric.
Isometric is very common in technical illustration. It shows 3 faces of the object equally, and parallel lines remain parallel. Dimensions along the main axis are true scale. It gives a good 3D sense while being somewhat measurable.
And oblique.
Oblique is another type where the front view is drawn true shape and the depth lines go back at an angle. A bit simpler to draw sometimes than isometric.
The most useful pictorial seem to be the exploded view drawing.
Oh, definitely. Especially for maintenance and assembly. It shows all the component parts of an assembly, separated out but aligned along axes, showing how they fit together.
Like seeing a machine disassembled but hovering in place.
Exactly. Perfect for understanding assembly order and identifying parts. You see them constantly in parts, catalogs, and repair manuals. Those are incredibly helpful.
They really are. Okay, next category, diagrams. The focus here shifts from physical shape to function.
Correct. Diagrams illustrate how things work or connect within a system rather than what they look like.
4 main types mentioned: installation, schematic, block, and wiring.
Right. Installation diagrams show the physical location of components within the aircraft.
Or is this black box?
Or is the cable run.
So spatial relationships in the aircraft. What about schematic diagrams?
Schematics are about function, usually electrical or fluid systems. They use standardized symbols to represent components, resistors, pumps, valves, and lines to show how they're connected and how the system operates. They don't show physical location, just the circuit logic or flow path.
So great for troubleshooting, understanding how the system should work.
Exactly. A technician uses a schematic to trace a signal or figure out why something isn't working electrically or hydraulically. Then they might use an installation diagram to find the actual faulty component.
Okay. Block diagrams.
These are very simplified. They represent major components or functions as simple labeled blocks, with lines showing the relationships and flow between them. Good for getting a high-level overview of a complex system without getting lost in the details.
Like a system flowchart.
Sort of, yeah. And finally, wiring diagrams. These sound detailed, very detailed. They show the actual electrical wiring. Every wire, its connection points, terminals, wire numbers, colors, connector pin numbers, everything needed to wire up a system or troubleshoot specific circuits. They can get incredibly complex on a modern aircraft.
Wow. So diagrams focus on function and connection. Then we got into the real nitty-gritty lines and their meanings. It's amazing how many types there are.
It's a visual alphabet, really. Each line style and thickness has a precise, standardized meaning. Using the wrong line type can cause serious confusion.
Okay, run through some key ones. Center lines.
Thin lines, long dash, short dash pattern indicate the center of symmetrical objects or paths of motion.
Dimension lines and extension lines.
Dimension lines are thin, solid lines with arrowheads, showing the extent of a dimension. Extension lines are also thin, solid lines extending from the feature being dimensioned, so the dimension line doesn't touch the object directly.
Sectioning lines.
Those are the crosshatch lines we talked about, indicating a surface cut in a sectional view. Usually thin, parallel lines, often angled.
Phantom lines.
Thin lines, one long dash followed by two short dashes, used to show alternate positions of moving parts or adjacent parts that provide context or repeated detail.
Break lines.
Used to shorten the view of long, uniform objects so they fit on the drawing. Short breaks are thick, wavy freehand lines. Long breaks are thin, straight lines with zigzags.
Leader lines.
Thin, solid lines, usually with an arrowhead or dot, pointing from a note or dimension to the specific feature it applies to.
Hidden lines.
Medium thickness, short, evenly spaced dashes. Crucial for showing edges and contours that are hidden behind other surfaces in that particular view. Helps you understand the 3D shape.
And outline or visible lines.
These are the thickest, solid lines on the drawing. They represent all the edges and contours of the object that are directly visible from that viewing angle. They define the main shape.
There were others too, like stitch lines, cutting plane lines. It's a rich vocabulary.
It has to be, to convey complex information clearly and unambiguously.
And complementing the lines are drawing symbols, the shorthand you mentioned.
Exactly. Standardized graphic representations. Saves drawing the same complex thing over and over and ensures everyone recognizes it.
Like material symbols.
Yes, specific crosshatch patterns used within section lines to indicate what material the part is made of: steel, aluminum, rubber, etc.
Shape symbols.
Sometimes used with sections, like a symbol indicating a diameter or radius to clarify geometry.
And electrical symbols must be huge.
Oh, absolutely. There's a vast library of standardized symbols for every conceivable electrical component. Resistors, capacitors, transistors, switches, relays, motors, lights. Essential for reading schematic and wiring diagrams.
Okay, so once you start to grasp the lines, the views, the symbols, how do you actually go about reading and interpreting drawings effectively? The chapter gave a process.
Yes, a systematic approach is key. Don't just jump in randomly. First, read the title block carefully. Check the drawing number, the name. Make sure it's the right drawing for the aircraft or assembly you care about.
And check the revision.
Crucial. Make sure you have the latest approved version. Then look at all the views provided, the orthographic ones. Get a general sense of the object's overall shape by looking at how the front, top, and side views relate.
Mentally assemble the 3D image.
Exactly. Then start focusing on the details. Understand what the different lines mean: visible, hidden, center lines. Trace features across different views to confirm their shape.
And then look at the numbers.
Yes, study the dimensions and tolerances carefully. Note whether they're in inches or millimeters, decimals or fractions. Check for any general print tolerances that might apply if a dimension doesn't have a specific tolerance.
Don't forget the notes.
Never forget the general notes, the material specifications in the bill of material or title block, any flags pointing to specific notes. Read everything. It's like detective work. You need all the clues.
It really does sound like piecing together a puzzle. The chapter also mentioned drawing sketches. These aren't formal drawings, but still important.
Very important, especially in maintenance and modification. A sketch is a quick, often freehand drawing used to convey an idea, document damage, or propose a repair.
So if a technician finds unexpected damage, they might sketch it.
Yes, to communicate it clearly to engineers or to plan the repair. Even though it's a sketch, it should still follow the basic rules, use appropriate views, clear lines, add necessary dimensions. Clarity is still key.
Enough detail for someone else to understand or even make a part from it.
For simple repairs or modifications, sometimes yes. The sketch needs to be accurate and contain all the critical information.
Makes sense. Then we had a quick look at other graphical tools, graphs and charts, nomograms.
Right, just other ways to present technical data visually. Bar graphs, pie charts for comparisons. Nomograms are interesting, those charts, with scales where you line up known values to find an unknown one.
Like the fuel calculation example. Handy graphical calculators.
Pretty much. And, of course, understand any notes or legends with graphs and charts.
And briefly, microfilm and microfiche. Legacy stuff.
Mostly legacy, yeah. Old methods for storing lots of drawings compactly on film. You might still need readers for very old aircraft data, but it's mostly digital now, CDs, DVDs, online databases.
Finally, digital images, like photos from a technician's phone.
They can be incredibly useful, documenting cracks, corrosion, the condition of a part, even proposed design schemes. The key, as the chapter stressed, is context.
Meaning?
Include a scale in the photo for size reference, and clearly state the location, which aircraft, which station number, which component. Just a photo isn't enough. It needs data with it to be truly useful documentation.
Okay, wow. That really covers the landscape. Back from the history to the digital present, looked at types, sections, title blocks, lines, symbols, diagrams. It's clear these drawings are absolutely foundational.
They really are the language of building and maintaining aircraft. It's this incredibly detailed, standardized communication that underpins the safety and reliability we expect.
Yeah, that level of meticulous detail directly translates into safety, doesn't it?
It has to. From the designer's initial concept right through decades of service, these drawings ensure everyone is working from the same accurate information. Understanding them, even the basics, gives you a real insight into the complexity and precision involved.
It really does. It unlocks a deeper understanding of how these amazing machines work and stay working.
It's the foundation for everything else, really, even as technology advances.
So here's a thought to chew on then. We're seeing more and more advanced tech digital twins, where there's a complete virtual model of the physical aircraft and augmented reality for maintenance, overlaying information onto the technician's view.
Yeah, fascinating developments.
So how might the principles we've talked about, this draftsman's language, how might that evolve as these new technologies take hold?
That's a great question. The fundamental need for precise, unambiguous geometric definition and technical specification won't go away. That's core engineering.
But the way it's presented might change.
Drastically. Maybe instead of interpreting 2D views, future technicians will interact with a 3D model directly, perhaps through AR glasses. The drawing might become a dynamic, queryable dataset integrated with real-time sensor data from the aircraft.
So the literacy required might shift, from interpreting lines on paper to navigating complex digital models and data streams.
It seems likely. The core principles of geometry, tolerance, materials, assembly logic, those will persist. But the interface, the way we access and interact with that information, could look very different. It's an exciting area to watch.
Definitely something to think about. If listeners want to see more, maybe check out Aviation Museum archives or online resources from standards bodies.
Good ideas. Or even just looking closely at illustrations in aircraft maintenance manuals gives you a taste. Seeing real-world examples really brings it home. Connecting with people in the industry, engineers or mechanics, can also offer great insights.
It really reinforces how vital this skill, this understanding truly is.
It's that baseline knowledge. It provides the framework for understanding pretty much everything else in aviation technology, old and new.
Well, thanks for joining us on this really detailed deep dive. Hopefully everyone listening now has a much clearer picture, pun intended, of the essential language of the skies.